Okay, so in this video I'm going to have a look at geometric sequences and series. Now a geometric sequence, as opposed to an arithmetic sequence which we did earlier in a previous video, geometric sequence is also known as a geometric progression, and it's just simply a set of numbers where each term after the first is found by multiplying the previous term by a fixed non-zero real number called a common ratio, or just OR. So for example, if we take the numbers 2 and we multiply, if we take 2 and we multiply it by 3, we get 6. If we multiply 3 by 6, we get 18, and so on. We just keep multiplying by 3 each time. So our common ratio, OR, will be 3, and our first term will be 2. So say we call this one term 1, this is term 2, this is term 3, and so on. So you can find any particular term by just keep multiplying by 3, each term by 3, to find the next one. Now that's okay if you want to find a fairly low-lying number here, the 9th or 10th number, that's fine. You can just keep multiplying by 3 until you get to that number. However, if you want to find, say, something like T150, the 150th term, for example, you're going to be multiplying by 3 for quite a while. So it's good to have a formula, as we did with the arithmetic sequence and series. So to work out the formula of Tn for a geometric sequence, what we need to do is, let's just say we'll work out the first 5. Let's say T1, T2, T3, T4, and T5. If we take our first term here is 2, and 2 is just called, generally speaking, this will be called A. We'll give it a letter A, and remember 3 here is our common ratio, OR. So T1 here, just make that a proper 1 here. So T1 is just simply going to be A. Now to find T2 here, we multiply by OR, so it's just going to be A times OR. To find T3, term 3, we multiply this term by OR, so we get A times OR, which is AR squared. To find the fourth term, we multiply this term here by OR, so we get AR squared times OR, which is AR cubed, and so on. This will be AR to the power of 4, and so on. Now, if we continue this on here and say we go on to term n, if you look at the pattern here, the OR here is to the power of 1, and our n is to the power of 2. The OR here is to the power of 2, and our n is to the power of 3. So the power here is always 1 less than the n. So we have 5 here as our n, and our power here is 4. So if we continue on along here, we'll see that it's just simply our nth term will be a or to the power of 1 less than the n, or n minus 1. So our general formula then is just simply going to be Tn is equal to a or to the power of n minus 1. So this is the formula we're going to use when we want to work out any particular term in a geometric series. So for example, up here we were looking at T150. So let's see if we can work that out. Well, that's just simply T150 equal to A, which is 2, times OR, which is 3, and we just simply raise that to the power of 149. So that will give us some big number. It's something like 2.47 rounded by 10 to the power of 71, actually. It's quite a big number anyway. So this is how you work out any particular general term of a geometric sequence. Now, if we want to work out the sum of the first n terms, so if we have for example 2 plus 6 plus 18 and so on. This is a series, this is a geometric series. Same as up above, we're multiplying 2 by 3, multiplying 6 by 3, multiplying 18 by 3, and so on. But this time we're adding them, so if we want, this is a series, so if we want to add up the first 2 terms, or 3 terms, or 5 terms, or 10 terms, how do we do that? Well, there is a formula again, and it is called Sn. So it's the sum of the first n terms, and it's given by a times 1 minus or to the power of n over 1 minus or. Now I'll just show you where this comes from in a minute. Now just remember as well, with this particular formula here, the 1 minus OR on the top and the bottom can be reversed. If the OR is less than 1, we'd usually write it this way. If the OR is greater than 1, you can write down OR to the power of n here and the 1 here. But just remember to reverse this as well. So it'd be a times OR to the power of n minus 1 over OR minus 1. This would be our Sn. You can write it this way either, depending on whether OR is greater than or less than 1. Okay, so where does this come from? Let's have a look at that. Well, if we take a series Sn, so we're going to take Sn is going to be just simply equal to a plus AR plus AR squared plus AR cubed plus and so on, all the way up to AR to the power of n minus 1. So this is one particular series here. And let's multiply the left-hand side and the right-hand side by OR. So you'll see why in a minute. So we're going to multiply this side by OR. So it's OR times Sn. Multiply this side by OR here. You get AR. So multiply A by OR, you get AR. Multiply this by OR, you get AR squared. Multiply this one here rather by OR, you get AR cubed, and so on, all the way up to A or to the power of n. So if you multiply this by OR, that'll be OR to the power of 1. So when you add the indices here, the ones will cancel, if you like, or you'll get 0. You'll just end up with AR to the power of n. So in other words, if you have AR to the power of n minus 1, and you multiply that by OR to the power of 1, so that will give you AR to the power of n minus 1 plus 1, which is just AR to the power of n. That's where this one here comes from. Okay, so at this stage what we're going to do is we're going to take these two series and I'm just going to subtract them. Okay, we're just going to subtract these two series here. So I'll just stick a line underneath them. So I'm going to take Sn. I'm going to take this minus this, and then take the top line here and subtract the bottom line here. So you just simply end up with A. This here and this here will cancel. This will cancel with this. This will cancel with this. All the way up along here. This one here will cancel with the one just previous to this. So in other words, if you like, here we should have plus AR to the power of n minus 1. So that's AR to the power of n minus 1 here. So this here will cancel with this one here, and you're just left out here with plus AR to the power of n. AR to the power of n. Okay, sorry, not plus here. This will actually be minus because we're subtracting. This will actually be minus here. Because remember, it's this minus this, so this will be a minus here. Okay, so these will all cancel all the way out along here, or you'll just get 0, in other words, when you subtract these, and you'll get 0 when you subtract this one from this one here. You're just left with the AR to the power of n at the end here, but with a minus in front of it. Okay, so let's take this this line here. So what we've ended up with is Sn minus or Sn is equal to A minus AR to the power of n. Now factorize this here. We've got an Sn here and an Sn here, so let's just factorize that. That's Sn is equal to 1 minus or here, and A minus actually what we'll do is we'll factorize the right hand side as well. That will just make that a little bit quicker. So we've got an A here and an A here, so take that outside the bracket. It's 1 minus r to the power of n. So A times 1 is A times r to the power of n is AR to the power of n. Now here we want a formula for Sn. So we can see here this Sn is multiplied by this here, so we're going to divide by 1 minus r. So Sn is equal to A times 1 minus r to the power of n all over 1 minus r. So this is the formula that I showed you at the beginning of this section here. So this is a formula for adding up the first n terms of a geometric series. Okay, so let's just finally do an example. So let's have a look at Tn equal to 12 times 4 to the power of n minus 8. Let's have a look at this particular geometric series here. What we're going to do with this is we're asked to find term 1 and then calculate S13. What do we get when we add up the first 13 terms of this particular series here? So how do we find T1? Well, this is Tn here. This is our general formula for Tn. So let's do T1 then. So instead of the n, we're putting in 1. So that's 12 times 4, 1 minus 8 up here. N is now 1. So this is 12 times 4 to the power of minus 7. So 12 over 4 to the power of plus 7. And that will just give us, let's see, what does that give us? 1. When you do that, you end up with 1 over 1032. So when you look for the first term, put in 1 instead of n. This here is our first term here, 1 over 1032. Now to calculate S13 then, so if this is our first term of this geometric series, what would S13 be? What do we get when we add up the first 13 terms of this particular series? Well, we know that A, remember this is T1, so that's A here, that's our first term. So our formula is A times 1 minus r to the power of n over 1 minus r. So our A here is just simply 1 over 1032. 1 minus whatever our r is. Now if you look at our original formula here, this is the formula we're given here. So our r here is actually 4. This is our r here, 4. So we just simply stick in 4 to the power of 13. That's all over 1 minus 4. So again, this is just a simple calculation that you can do on your calculator, and you actually get 21675.99. So when you add up the first 13 terms of this particular series here, this is what you get here. Okay, just one last thing before we leave it. If you're given a particular term number, say Tn is equal to 1/3 to the power of n. So this is our general term of a particular geometric series. What we want to do is prove that we want to prove that this is geometric. Now remember, in an arithmetic sequence, like for example, let's say 2, 4, 6, 8, 10. This is arithmetic, okay, as opposed to geometric. We're adding 2 each time, so it's a linear sequence or an arithmetic sequence. To show that this is arithmetic, you can just do this kind of thing here. You can subtract 2 from 4 and you get plus 2. Subtract 4 from 6, you get plus 2. Subtract 6 from 8, you get plus 2. Subtract 8 from 10, you get plus 2. And so on. So we can see that the first change or the first difference is plus 2. We're adding 2 to each term. So this is arithmetic. Now with geometric, we're multiplying each term by a constant. So to prove that this thing here is geometric, what you do is you take any term, you take any particular term, Tn, and you divide it by the previous term, Tn minus 1. If that's a constant, then it's geometric. If what you get when you divide any term by a previous term is not a constant, then it's not geometric. So how are we going to prove this? Well, this is Tn here. This is any particular term. What we need is Tn minus 1. Tn minus 1 is just simply going to be 1/3 to the power of n minus 1. So let's divide these two and see what we get. So we have Tn over Tn minus 1. So that's going to be 1/3 to the power of n divided by 1/3 to the power of n minus 1. So that's just by our laws of indices, our rules of indices here. We're dividing two numbers to the power, 1/3 to the power of n, 1/3 to the power of n minus 1. So we subtract the powers, in other words. So that's just going to be 1/3 to the power of n minus n minus 1. So that is 1/3 to the power of n minus n plus 1. So that's just simply 1/3 to the power of 1, or 1/3. So 1/3 is a constant. It doesn't change. It doesn't have an n in there or an x or y or any other letters. It's just 1/3. So because it's a constant, this particular series here, or sequence if you like, is a geometric sequence. And that's it.